So we will use this problem as an example. Look, I will take a picture, that way I will not have to go back to this one. Okay, go to our whiteboard. So we will pick the information as it is stated in the problem. So let me just make this bigger. So Snake Eyes Magoo is a man of habit, meaning he does this every week, or whatever he does, he repeatedly do it. For instance, his Fridays are all alike. So every Friday evening, he goes to the joint with his week salary of $180, steady gambling for 2 hours, then home to his family, leaving $45 behind. So quite a very long statement, but we will get the given information from this statement, okay? So not much to pick from the first statement because it's just speaking of his being a man of habit. So what is important here is the second. He gambles every Friday evening with his week salary of $180 for 2 hours. Then home to his family, leaving $45 behind. So how would you interpret this information? He goes to the gambling joint with his week salary of $180, gambles for 2 hours, then goes home to his family, leaving $45 behind. How would you interpret this information? Anyone? If we will compare the salary to, let's say, concentrations, and the time here is still time, how will we write down the information in this case, provided in the problem?
Miss,
Yes.
I think, Miss,
Sige,
it's
go.
initial concentration.
Initial
Initial
concentration.
concentration, CAO, is 180.
Okay, very good. Then,
Time is 2 hours. And the final concentration would be 180 minus 45, which is 135.
very good. So your final concentration is 180 minus 45. So let me go back to the statement that will validate that one. So it says here that after 2 hours, he goes home to his family, leaving $45 behind. So, gimbili niya sa gambling joint ang $45. So, what he has is the difference of 180 and 45, and it's actually 135. So, I'd like to have here 135. Okay? By the way, if you're going to interpret in terms of kinetics, the $45 that he left behind, what is its representation? How would we represent it in terms of kinetics? The $45 that he lost or that he left behind in the gambling joint. That would be the what?
CAOXA.
Very good. Very good,
COX.
Joshua. That would be the amount that has been converted, or in this case that has disappeared because he lost it. So that would be the 45. So if you notice, class, the initial concentration minus the amount that was left behind or that was lost due to gambling will give the amount that he brings home to his family. So this is for 2 hours of gambling. So that's for that particular statement. So I will again read what we have here. So he always bets in amount proportional to his cash at hand, and his losses are also predictable at a rate proportional to his cash at hand. Now, this particular statement is very important because this will tell you what is the appropriate rate expression. It says here, he always bets in amounts proportional to his cash at hand, and his losses are also predictable. Ano ang predictable? It is at a rate proportional to his cash at hand. So how will you translate this particular statement into a rate expression? his losses are proportional to his cash at hand. And he always bets in amounts proportional to his cash at hand. Would this mean if we will compare it to a practical scenario, kung dako pa iya kwarta, kusog siya maperde. Kung kay kusog siya magbet. Kung gamay niya kwarta, gamay man siya magbet, gamay man niya perde. So how will you compare it or how will you represent it in terms of a rate equation? Would it be correct if we say that, so would it be correct that if we say that the rate of change of his money, yeah, CAO ta, so that would be this one, is proportional to his money. Why is it proportional to his money? Isn't it that his losses are the rate in which he is losing is based also on the amount that he has left? So the rate in which the amount of money that he has changes is proportional to his money. In this case, the money that he has left. So in terms of kinetics, this is how we can represent his betting pattern or his losing pattern. He is losing because this is negative, meaning that he doesn't win. He always lose. So he is losing in this particular pattern. Why he is losing? Because it's stated in the problem that he always live, as usual, $45 behind. So, kaperde gid siya, kaya ginabili niya, ginatuya mo, unta siya, meaning, nakaperde na siya, $45. So, this is your rate expression. It's comparable to a first order differential equation. Comparable to a first order irreversible chemical reaction. So if we would change the proportionality equation later in the solution, we will introduce already the rate constant because we're taught that whenever the proportionality symbol is omitted and replaced by an equal sign, you have to introduce a certain constant. So that would be in this case our rate constant, okay, for this problem. So I will read further. So that's what we got from that particular statement, that information. Then it says here, this week Snake Eyes received the raise in salary. So he played for 3 hours and hindi siya mag-change out. Okay, he played for 3 hours and he went home as usual. The term is as usual, went home with $135. So meaning, per day man gyapon niya again, raise niya salary. Kaya iya per mi bit kakuli is $135. The question is, how much was his raise? So we'll have here the required information. How much was the raise in salary of Snake Eyes and Magoo? Okay? That's our unknown. How much was his raise? Given that he played this time for 3 hours and the $135 is still the CA. So the term is went home as usual, went home with $135. So that's the remaining money that he has. Okay, so this is our given, that's our required. Now we go to the solution to this problem. So we'll have another one here. So we go to the solution. Now, I will start from here. So we'll have negative dCA dt. Now I will introduce the KCA. Okay. And then if we will process this one, you know that this would be negative dCA over CA, separation of variables, K dt. you have ln of Ca over CaO is equal to negative Kt. This is the formula that we have for irreversible first order reaction. Okay, now given the information that we had here, the CaO and the Ca for 2 hours, we'll be able to find the K. So the ln of the Ca, he always have 135 left. The CaO is 180 in the first scenario. No raise yet, no raise in salary, equal to negative K. The time for playing is 2 hours. So in here, you'll be able to find the rate constant. What do you think is the rate constant? Okay, so it's
0.144.
144. Correct. Thank you. Per hour. So that would be now our ln of Ca over CaO equal to negative 0.1440. This is the equation that we'll be using. Now, when he has the raise already, we do not know the initial money that he has. Okay, so in the second scenario wherein he already has a raise, we have ln of Ca. Your Ca is still 135 because he goes home with that amount of money, meaning he stops when he already has 135 left. This week, he has a raise. We don't know how much was his initial money when he went to the joint. And we have 0.144 here, by the way, negative. And he played for 3 hours this time. So you'll be able to determine here the initial money that he has when he went to the joint, gambling joint, in this week wherein he has the raise. And that would be 207.82. So as to the raise, what is the raise? Is this correct? 207.82. So his raise would be his salary this week, wherein he has the salary, the raise minus the original salary that he has with no raise. So the raise is 27.82. So this is Snake Eyes Magoo's raise for this week, $27.82. You get it? Any questions so far? So we can go to the next lesson. No question. I think we have enough here. So we will go back to some of the problems later on wherein we can apply already the determination of the N and K. So we will have now the new slide. Okay. So we will proceed. And we're now on the methods of determining the N and K. And the first one would be determining it empirically. Why it has to start here. Okay, you're here already. Okay, methods of determining the N, the order of the reaction, and the K, the rate constant. And the first part here, or the first method, is using the empirical rate equation, wherein you generally write N as N. So the empirical rate equation of nth order is given by this. Okay. Wait, class, hindi siya mag-open. Let me share again. I will stop sharing, class. I will just share raw without the projection on my slides. Okay, so this is your rate equation, wherein the order of the reaction, which is n, represented by n, and the rate constant is k, is written generally. You do not know the n, you do not know the k. So what you did, you simply transferred the c sub a raised to n expression here under the dCA and process the corresponding differential equation as is where is. And there's a note here that n is solved by trial and error. So I will start here. I will start from here. So if you will have a rate expression, a differential equation in which k and n are written generally, you separate variables, then you integrate. When you integrate this will be using power rule. And this one will be integral of k dt from 0 to t. Okay, when you use power rule for this, so we are in integral calculus, we add 1 to the exponent. So CA raised to 1 minus n minus CAO raised to 1 minus n. All of this will be divided by 1 minus n. Whatever is the corresponding exponent, that is the denominator of your variable in integral. So you have to add 1 here to the exponent. Both of this now, the upper limit and the lower limit, will have a denominator of 1 minus n. And that's negative. So we can place actually the negative here, or we can place it here on the other side. Now, if you integrate k dt in here, so that would be kt, knowing that your limit would be t minus 0, and that would be 0 for the lower limit, so you only have kt. Now, so that we won't have a negative here, we can write that expression as Ca raised to 1 minus n minus CAO raised to 1 minus n all over n minus 1. Already taking away the negative sign in here, and this should be kt. Now, how will you deal with such an expression as this? Now, we know for one, I have already mentioned in the first part, in the guessing and testing of the plot of the empirical data, that when we talk about a particular reaction, this k and this n is fixed. So even if you have 10 set of data or 5 sets of data, those data should still arrive at the same k and n. So what we do with this method of empirically writing or determining the k and the n based on this general formula, we solve for the k. So you have k, you have here Ca raised to 1 minus n minus CAO raised to 1 minus n. This t you'll place here, and you have n minus 1. What you do is, based on this formula that you have with the initial concentration provided in the problem, let's say the problem gives you, let's say you have Ca and you have time, okay, example, and you have several values here. So you're going to test, you are going to rather guess a value for n that you will place here. You substitute the Ca that you have here, for example, and the time that you have here with the n that you have chosen to use first, you solve for the k. That k value that you have, you compare with the k value that you will be getting on the next pair of data, using the same n that you use for determining the k here on the first. If that particular n that you used here in determining the k in the first set of data will not arrive at the same k for the second data, you have to change your original guess. But there's no plotting here. You just simply guess an n, substitute, solve for the k, and that k should be uniform for all pairs of data that you have here. For all the data that you have, that k should be uniform. Now, question is, how can we say that more or less They are uniform. So if you have, let's say, if you solve for the value of k up to 3 decimal places, the first 3 numbers that you have until the thousandth place, that is, of your decimal value should be the same. Doesn't have to be that the fourth, the fifth, and the sixth value of your k should be the same. Of the number of your k should be the same, as long as the first 3 numbers in your decimal value for k is the same. That is already acceptable, meaning whatever n you have assumed in determining the k, that is already acceptable. Okay, this is in the case of using this particular method, because there are other methods other than this one. The beauty of this method is you don't have to guess and test and plot. You don't need to plot your empirical data and then check whether your plot is a straight line. You just have to simply guess an n. Okay, to illustrate what I mean, we'll pick a problem from Levenspiel where we can use this one in testing the n value that we got for all sets of data provided. Okay, let's see. Levenspiel, where are you? Okay, let me see. Wait a minute, class. Minute, 1/2 order. It's already known, so we have to use another problem wherein the n is not known. We can have 3.5, but that's only 2. So let's say we'll have another one. This is half-life. That's another one. Okay, let me check if I have already a solution for 3.11, because it will take us a lot of time if I did not have it solved initially. That way we will not waste time on determining the n. Okay, 3.10. Okay, so we can start with 3.11. This way we have, shall I say, 5 sets of data there, the CA and the T, in which we can use the empirical equation that we have derived. But before that, there are very important generalizations that I would like to share first before we solve that problem. That we need to consider. So if you have already, let's say, open. So this is our empirical rate equation. Now this would be the generalization. Excuse me, class, it's not showing the exact thing. I will not just have it projected. Okay, so I will show this one first. Do you see my screen?
Yes, miss.
Okay, so this, do you see the screen now for the empirical rate equation of nth order? Do you see this?
Yes, miss.
Okay, so this is the rate expression that we had. What I just did in the whiteboard is to isolate the k on one side. That way we can solve for the k's based on the n values that we have guessed. Okay, now these are the generalizations that I mean, which are very important to take note of when we use this particular method of finding the n. And then, of course, after finding the n, we can find the k. Now, for reactions with n greater than 1, if you use this method, 100% completion is not attained in finite time. So if the order of the reaction that you have arrived at after guessing and testing for all pairs of data that you're provided has a value greater than 1, you cannot, this could be rephrased as you cannot determine the exact time in which your XA will be 1.0, because it says here 100% completion is not attained in finite time, meaning using the method, you cannot determine the time in which all of your reacting species are 100% converted. Now, if the reaction order that you have also determined, on the other hand, if it's less than 1, reactant concentration will fall to 0 and then even become negative at some finite time. And just like if you recall my discussion a while ago with zero order reactions, that if the problem asks you to determine the concentration of A, for example, for T greater or equal to CaO over K, the Ca value that you will be getting is negative, meaning that tells you that at that time that the problem is asking you to determine Ca, there is none left for Ca anymore, meaning it's already 100% converted. That same principle is applying to this method of determining the rate law and determining the n using the empirical rate equation. There would be instances, especially if the order of reaction that you have arrived at is less than 1, wherein the value of Ca will become 0 and even negative when you compute it at this particular condition. So what will you do then? That way you will not get, let's say, confused, or you will like panic. Why is it that my concentration is negative, especially when you're solving for it? Or is there something wrong with what I'm doing? Why is this negative? I did everything right. It's because you also have to check in this case, based on this condition, that whenever the initial concentration and the problem is raised to 1 minus n, the n that you have arrived at or solved at, divided by 1 minus n times k, if the t that is being asked in the problem is equal to or greater than this one, this value here that you have computed, expect that the Ca that you will be getting will be negative or even 0. If that is the case, you can simply answer that your Ca is equal to 0, because then you have to place this particular how shall I say, proof. You put this proof, since the time in which the problem is providing is greater to than this one, then it follows that the Ca is already 0 at that particular time. That is class only if the n that you have guessed is less than 1 and it is already correct. But if it's greater than 1, this one you need not use as testing. Well, now, if you will have a problem with, let's say, n equal to 2.5, and then the Ca that you got is negative, then you have really a problem with that. Because in n greater than 1, you will never have a Ca which is negative or 0 given the time that is given in the problem. It will not be a value that will fall to negative or 0. It's only for n less than 1. Now, in real systems, the observed fractional order, if this n here is fraction, meaning it's less than 1, shifts upward to unity as reactant is depleted. Now, this is very important that you understand this. In real systems, meaning on a real scenario, what is really actually happening, that whenever your order is fractional in nature, as the reactant gets depleted, meaning Ca is approaching 0 or Xa is approaching 1.0 or 100% conversion, this fractional order shifts upward, meaning the order itself changes. in real systems. So your fractional order, which is 1/2 or 1/3, as your reactant gets depleted, that particular order changes. That's for real system. But you need not worry about that, because this 2 is already enough for you as a guide, whether when you validate your answer later on, are my answers acceptable or not. So you have to use these 2 points in here. This is just written here in real scenario. Anong gakatabo? Your order actually increases if it's a fractional order. If it's not 1 or 2 or 3, it increases when the reactant gets depleted, or when you're nearing 100% conversion of your reactant. So that is in the case of the use of this particular method. So now we're ready to go back to that problem that we can use this method to solve. Okay. Now in 3.11, you're given an aqueous A at a concentration of 1 mole per liter initial, that is, which is introduced into a batch reactor where it reacts away to form product R according to this particular reaction. The concentration of A in the reactor is monitored at various times as shown below. So these were the concentrations at various times. For CaO equal to 500 mole per cubic meter, what if, this is the scenario, you are to find the conversion of the reactant after 5 hours in the same batch reactor? So this is the scenario. This is how the concentration changes with time when you start with an initial concentration of 1 mole per liter. So the problem now is asking, what if you start with a different concentration? What would be the corresponding conversion after 5 hours? Now, you can only answer this if you already have the correct rate law that will represent this particular empirical data together with the initial concentration. And that's the thing that we need to find initially. That way we can answer the question or the required information. So we go to the board and then determine the required information in this case. So this is your 3.11. So you have this as the given information. A forming R, initial concentration of A, which is 1 mole per liter. Then you are given this table, the T in minutes, and CaO in mole per cubic meter. Now you have 0 here, 1000 initial, so this is your initial concentration. And you have 100, and you have 500, and you have 200, you have here 333, you have 300, and you have 250. So there's a decrease in the concentration, and you have 400, and you have 200 here. Okay, so this is your data. So you are required for a CaO equal to 500 mole per cubic meter at T equal to 5 hours. What's the conversion? We're talking of the same reaction here. However, we started with a much larger a smaller concentration, because this one is in liter, this one is in cubic meter. So 500 mole per cubic meter. This one is 1 mole per liter. So you could see here that this one, the unit here is mole per cubic meter, while this one is already in liters. But these two are just the same. So given this data, we need to find the rate law first before we can answer the unknown. Okay, so we go to our solution. So our solution, of course, will start with the formula that we will use. So I have written the formula here. Let me go back to the... I have written the formula here. This is the formula. So we will use that formula on the other side, on the next slide. So we'll have K being equal to Ca raised to 1 minus n minus CAO raised to 1 minus n. Then I have n minus 1 times t. Let me check. N minus 1, not 1 minus t. Okay, correct. So n minus 1 times t. So this is our equation. So what we'll do, we will use the pairing that we have here. So since this part is referring to the initial concentration, we will not use that anymore. We'll not use that anymore because anyhow, it's already here that at time 0, your initial concentration would be 1 mole per liter or 1,000 mole per cubic meter. So I will start with this, and this. I will check, I will determine my K1, my K2, my K3, and my K4 based on the guesswork that I have made. I will guess for an N. Now this K1, K2, K3, and K4, they should be equal. So my K1, K2, K3, and K4 should be equal for this 4 set of information. So we will do just that. Let's say, for example, what did my first guess here? Oh, we'll start with a guess that is far from what my answer here. So you could see. So let's say, for example, I will start with an N. Let's say if N is equal to 1. Okay. So based on my K1 should be equal to, so this is the K formula that we have here. So we have 100, we have 500 after 100 minutes. So I will have here 500 raised to, oh my God, 1 minus n, 1 minus n minus 500. Wait, guys. My initial concentration here is 1,000. Why did I write 500? 1,000. So this should be, we'll change this. So 1,000. And I cannot, by the way, class, but good that I have placed it here. I cannot, by the way, use n equal to 1 because automatically all my exponents will be equal to 0. So using this method of empirically determining the n and the k, you cannot use n equal to 1. So we will make it 1.5. That way, I will not have a 0. So this is 1 minus n over n minus 1 times the t in this pair of data is 100. So 100. So I will solve for my k now. So I have 500 raised to 1 minus 1.5. So that's negative 0.5 minus 1,000 raised to negative 0.5 all over zero point 0.5 in this case. 1.5 minus 1 times 100. Kindly solve for the k value here. I will have another k here, my k2, for a different set of value, which is 333 and 200. So I will have here 333. That would be 1 minus 1.5 still minus 1,000 raised to 1 minus 1.5 divided by 1.5 minus 1. This time, my time is 200. So I will have also a k value. Can you compute for the corresponding value of the k's here? If they're not equal, then there's no point in proceeding with the rest of the values that you are provided. So you have 100 or 500 raised to We divide that by divide 0.5 times 100. What's the K value that you got here, K1?
For me, Miss, 2.6197 times 10 to the negative 4.
-4. Okay, same here, same here. So I'll just change here to 333. Kung na ano, change yun na lang, may formula naman kamo, then 1,000, then you have 0.5, and you multiply it by 200. So here, in the second, you will have 2.318, 77, right? Times 10 raised to -4. If let's say, for example, just for ano, K3, your set of value for K3 is 250 raised to -0.5 minus 1,000 raised to -0.5. This is 0.5. Your time for that is 300. What do you think is the K value here? We'll see. So it's 250, 250, and then you have 300. Your answer is 2.1082 times 10 raised to -4. Although they all starts with 2, but quite different. So if you're going to write this in decimal, this is 0.000262. This one is 0.000232. This one is 0.000211. Okay, that would be the three values. So if you think that's okay, your first guess is okay, then you can go ahead. But what if we change this to 2? So I'll change this to 2. I will have another guess, which is n equal to 2. So if your n, class, if your n is equal to 2, if n is equal to 2 using the same K formula, you will have 500 raised to 0.5 negative minus 1,000 raised to 0.5. You have 0.5 times 100. This is, sorry, why did I place the 0.5? This is already order 2. So if n is equal to 2, k is equal to, so I will have a CA of 500. So this would be -1 because it's 1 minus 2. This would be 1,000 raised to -1. This would be 1 times 100 for K1. Okay. For K2, we'll be using the 333 raised to -1 minus 1,000 raised to -1. This is 1 times your time here is 200. So you will have, let's say at K3, we'll use the third one. We have a 250 raised to -1 minus 1,000 raised to -1 over 1 times the time here, which is 300. So you'll be getting K values. Let's see, what's my value for the K here? Can you check your value also? My value is 1 times 10 raised to -5. We'll see. I'll change this to 500. And the denominator, this should be -1. This should be -1. And the denominator should be 1 times 200. So, is it wrong? Is it, why is it my answer different? What's your answer, class?
K2 lang different, miss. Ang K3 kay K4 pareho.
K1 is What's K1?
Amo na, miss.
1
times
times
Ano,
1
miss?
miss.
negative 5. Your
Yes, miss.
K3 is,
Amo man, miss.
A man miss.
ang K4, na-check niya,
Same man, miss.
same siya. What about K2? Pila answers ang K2?
1.0015.
0015.
Okay. 1.0015 times 10 raised to negative 5, yapon?
Miss.
It's okay. So if you're going to write this, compared to this two, this one is like 1, 2, 3, 4, 1, right? This one is 1, 2, 3, 4, 1. So may dua pagig ka 0, 2, like that. That's comparable already. So this is a case wherein you can settle with what you have guessed. So in this case, you can conclude that n is equal to 2. Okay? Very minimal. So actually, I have already rounded it off. It's just actually 1 here, 1, 5. So that's okay. 1.0015. Once you have already the second order here as the answer, then you can solve it using second order rate law. And if it's asking for, in this case, I'll go back to the sheet. It's asking for the conversion. So you use the formula for second order reaction case 2 because you only have a single species here. Okay. If you want, you can derive it better because you get to understand how it's going to be done. So you just simply write dCA dt is equal to k Ca raised to 2. If you're going to do the maths, that would still give you the same answer. So Ca squared negative, this is k dt. So if you will integrate from ZAO to Ca, this one 0 to t, you will have here a negative of Ca raised to negative 1 over negative 1 with the limit CAO to Ca. If you use power rule, so negative 1 over negative 1, this one would be a KT, of course, 0 to T. You want to, of course, these two take care of themselves. So you have 1 over Ca minus 1 over CAO being equal to KT. Now, the K that you will use here is the K that is common to the 3. So you will have 1 over Ca being equal to, minus, that's not equal, minus the CAO that is that is given in the problem in which you are to determine conversion. So that's 500. In that case, you will place here 1 over 500. And this is 1 times 10 raised to negative 5. The time here is 5 hours. Wait. There is an alternative formula that you can use in terms of XA, but if you started with that, it's okay, class. No problem. You can always solve for XA anyhow. So you're after for XA, after 5 hours, having to start with 500. So in this case, you have a CA value here. Can you solve for the CA? So 1 exponent negative 5 times 5 times 500. Your CA here is 40. So it's 40, what's the mole per cubic meter?
Ay, miss.
Yes.
Ang time bala, miss.
Ah,
Ang minutes sa miss.
Ay,
Hindi.
sorry.
I-convert pa ang hours to minutes.
Na-miss ko siya. Hindi lang, jobber na. Okay. Minutes siya galiho. So we change. We multiply pa. So this is lacking. We need, thank you, jobber. So this should be multiplied to 60. Okay, that's in hours. So the K that, by the way, the unit for the K that you got here, I'll write the K here. It's 1 times 10 raised to negative 5. Since the empirical data is in mole per cubic meter per minute, and this is a second order reaction, so this is cubic meter per mole per minute. So there's a need for us to convert here. So I am to change negative 5 times 5 times 60 times 500. So your CA is 1.5. Can you check, please? 5 times 60.
200, miss.
Sala akong solve. Yan lang. Plus 500. Yeah, it's 200. Thank you. So this should be 200. Okay. A 200 here. Now, if you have the CA, you can solve for the CAO actually. You need not go back to the formula that has the CA if you're started with this. You can solve for the rather the XA. So with a CA of 200 mole per cubic meter, we have a very fundamental formula. CA is equal to CAO 1 minus XA. This holds true for all reactions. So with a 200 here and a, what's our CAO in this case? 1000. What's our CAO?
700
1000.
ganun.
Yes. Wait ha, ang CAO naton
500 siguro, miss.
CAO, in the new scenario, it's 500. Thank you. So this should be 501 minus XA. So you'll be able to solve for your XA. So we divide by 500. That's a 0.4. So it's a 0.6. Sorry, it's a 0.6.
Yes, miss.
So your XA is a 0.6. Okay? XA is 0.6. I will give you an example on this on Wednesday. I will meet for only 12:30 to 1:30 on Wednesday. And the rest of the time, I will leave an asynchronous task for you to do so that I can give you more example on the application of this, and I can discuss the other methods as well of determining the N and K. Let me just share. I still have 2 minutes, just for a while. Let me share from my slides. If this is our general empirical rate equation, so that's method 1, empirical rate equation of nth order. The second is the same as that approach, but this time the problem gives you the half-lives. So it's not just any t, but rather it gives you the half-lives for different values of initial concentration that we will be discussing on Wednesday. So I can finish this part here. And the other method is using fractional life. So it's not only half-life, but the time it took for, let's say, the concentration to reach 1/3 or 1/4 or 1/5. So that is why it's referred to as the fractional life method. The second one is limiting because this will only cater to problems concerning half-lives, a problem that provides you with a half-life together with an initial concentration. So we will continue this on Wednesday. Let me see, what else do I have here? The different generalizations, and after that we will have multiple reactions, which I'll be discussing, I think, next week. Okay, so that's it for now, class. It's a minute before it's going to be 2:30, and I still have a next class. So do you still have any question for now as to what we have discussed?